Hello and welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. And today we have the paper VLN BERT, a recurrent vision and language BERT for navigation. And our guest today is Yicong Hong. Hello, Yicong.
Hi, Isaac.
Can you introduce yourself?
I'm currently a third year PhD student at the Australian National University, and I'm supervised by Professor Stephen Gould here, and Professor Le Xin Xie, also from ANU, and Dr. Chi Wu from the University of Adelaide. So I've been working on vision and language, especially vision language navigation problem for 2 years now, and I'm happy to share this paper with you.
So, who are the authors of the paper?
So I'm the first author, and this is a cooperative paper with my supervisor Chi from Adelaide, and then Yuankai, also from Adelaide, and Cristian, who is previously a PhD student at ANU, but now he's moved to AIML in Adelaide, and then my chair supervisor Stephen Good.
Okay, so let's start with the abstract or the TLDR portion of this episode. So, what is the paper about in 2-3 sentences?
Um, yeah, so in the paper, we introduce recurrence into the multi-layer transformer to keep track of a state representation for a sequential decision process. And we implement the idea onto the transformer pre-trained with vision language knowledge, and then we apply the network for the vision language navigation problem, which greatly improves the agent performance. And we call our method recurrent VLN BERT.
That was a mouthful. So let's break it down to pieces so the listeners can understand. So what problem is the paper addressing?
Yeah, so we're looking into the vision language navigation problem, or simply VLN. So the task requires an agent to navigate in previously unseen and photorealistic environments following human natural language instructions. So it is a very important problem, I think, because it is a important step towards building a interactive embodied AI that assists human in daily work.
So what are the main challenges in this domain?
I think it's how to train. It's basically how to learn about this cross-modal correspondence, right? How to know which part of the very complex human natural language is related to what the agent sees, right? The visual observation, basically. How to relate them together and then derive some useful information to achieve some tasks.
Okay, so let's just make it a little bit easier. So for the completely novice listener, you say cross model. So what are your input modalities? What is the input to your method?
So, for example, in the VLN task, the input are the navigational instructions, so which basically described how an agent should move forward, how it should navigate to a target. And then the other part of the input is the visual input, so basically RGB image of the scene.
So you have images and basically sentences, right? Text.
Yes, yeah, that's right.
And what is the output then?
The output is basically a sequence of actions that moves the agent towards the target.
And when you say agent, I'm assuming you're not meaning 007. So when you say agent, that refers to what?
That basically is a robot. It's a robot in our case, it's a robot in a simulated environment.
Okay, so what is the main contribution of this paper?
First of all, we propose, I think, a very simple but effective idea, which is to introduce the recurrence into this multi-layer transformer network. And we show that this transformer network itself can function as a recurrent network to keep track of a state representation. And we think this could be important because it can be applied to other tasks that require this sequential decision process. So not only navigation, but also like in dialogue scenarios. So apart from that, more technically, the second contribution I think is we actually propose a multitasking network. So we ask this recurrent transformer that we built to encode language inputs, the instructions, encode visual inputs, so the observations, and then learn about the cross-modal correspondence, and then function as a recurrent network, and then decision making. And then for the decisions, it even includes the actions for navigation and the object grounding for the referring expression task. So basically localizing an object while moving forward.
So before we dive into the method, if you had to choose one or two papers that are super relevant and anyone reading your paper should read beforehand, which papers would those be?
I think the attention is all you need paper always comes first, because it is where this self-attention and transformer and this pre-trained BERT model idea have originated from. And basically, they propose to stack the soft attention blocks vertically and horizontally to create this so-called multi-layer transformer, which is very simple and flexible model for learning these correspondences between inputs of the same modality or different modalities. And also, it turns out to be a great model for pre-training. It has achieved significant performance in almost all the natural language processing and vision language tasks. So now more and more people want to apply it for this navigation problem. Yeah, so that's the first paper. The second one, I would say, is the prevalent, which inspired our paper a lot. The title is Towards Learning a Generic Agent for Vision and Language via Pre-training. And in the paper, they basically pre-train a BERT model for encoding the navigational instructions in navigation tasks. But comparing to our work, we didn't do pre-training, and our focus is to investigate how could we make a pre-trained model better use the pre-trained knowledge.
Okay, so you mentioned a lot of very technical terms here. So now that we talk about the approach, let's try to break it down, right? You said transformer, attention, soft attention. Can you just briefly give the novice listener like a one sentence? What does it do? What does it mean?
Soft attention is essentially dot product weighting, basically. It was first proposed in, I think, in a paper called Show, Attend, and Tell, which is doing image captioning task. So you need to figure out which part of the image is most relevant, most salient to describe. So they come up with this attention idea to look at each part of the image and then to find out which part is most relevant. And that idea has been extended to many other tasks. For example, in natural language processing, we need to know which words are related to each other, because the words often work together to clarify a meaning, right? And as well as in vision and language, right? For the visual part, we can learn from the language which part of the image is most relevant to the language, to the instruction, for example. And in terms of the language side, we can learn from the image to know which words are the most important. So soft attention has become, I think, probably the most important mechanism in all the vision and language studies. And then about the transformer, which is basically to stack this dot product based soft attention blocks horizontally and vertically. So to allow it to go wider and deeper, to extract more high level and abstract information, to learn about this very deep relationship between the inputs. And it's very powerful.
Mm-hmm. Okay, I'm going to try to say it in my own words. Okay, so basically what you're saying is your input, your images and text have a lot of information. Some of it is important, some of it is not important. And basically what the attention mechanism does, it basically highlights or gives higher weight to the important stuff and less weight to the unimportant stuff. And that allows like the network to use that in order to make good inference.
Yeah, that's great. That's a much easier way.
Okay, so now let's talk about the approach. So yeah, so your input, you get your images, you get your instructions as text. What do you do next?
I think, as I said, we introduced this recurrent into transformer, right? And the way that we did it is actually use one of the input tokens as state representation. So we call the input to transformer network tokens. So for example, in our case, we have language tokens, which is basically each word in the instructions, and then the visual tokens, which are basically the agent observations. So usually people will just pass these vision and language tokens into the transformer, to get some better representations of these two inputs. But now, apart from the visual and language tokens, we add an additional state token to represent the agent state. And we keep passing this state representation at each iteration of this navigation process. And this representation will basically collect useful information from the language part and the new observation at each time step, while the past information stored in this state representation will also help the transformer to make a decision. So the transformer itself is actually pretty straightforward. We simply add this state token into the network.
So when you say make a decision, is basically where to go next, right?
Yes. And in our case, it's actually by selecting which navigable directions that has a image which is most relevant to the instructions. So, for example, if the instruction mention a table, then the image which has a table should be the correct direction to navigate.
Actually, I feel like we should talk about this in a context of an example. So can you give an example of an input and what is the expected output?
In the task that we are addressing, the instruction for navigation is actually can be either high level or low level, right? So low level means it's very detailed, very specific. Go to the table, turn left to the kitchen, pass the living room, and then stop at somewhere, right? So so the agent at each step in the environment will need to know, for example, which part of the instruction has been completed and what to do next, right? So for example, if it says go to the table and then enter the kitchen, if it already passed the table, then it should know, okay, now it's time for going into a kitchen. Right? So it will select the direction which is heading to the kitchen to navigate.
Yeah, that's a great example. So let me ask you this question. What is your favorite part of your method?
So yeah, I think the most important part is that we sort of validate a hypothesis that multi-layer transformer can actually function as a recurrent network, because I think no one has tried so before. Right? Everyone just use it as a encoder to generate some representations, but we think it is actually possible to use it just as using some other recurrent network like LSTM, long short-term memory, and because that it is very simple. So it can be applied to many different form of this transformer architecture. And in our paper, we actually tried on 2 different transformers, and they both work very well. And I think also because of the simplicity and efficiency, I think it has a potential to become a general model for some other problem rather than navigation. That involves what we call the partially observable Markov decision process. So basically a process that requires these sequential decisions.
Okay, so let's move on to the results section. So what are the experiments that you've done and you tested it on?
So I think our experiments memory includes 3 parts. So the first part is to evaluate on standard benchmarking datasets and metrics. So that's basically comparing with others. So we evaluate our model without pre-training, pre-train with general vision and language knowledge, and pre-train especially for navigation. So we compare all these 3 models with previous state-of-the-art networks to show the difference. So that's the first thing. The second is that we did lots of ablation study to show that it is actually the design that helps rather than just probably some noise that improves the performance. Right. So we start with a baseline network and we replace the components in this very simple baseline network with our transformer network. And then we found that, so we keep replacing the language encoder first, and then the language and visual encoder, and then we introduce this state representation, and then we use it to do decision making. So we did it step by steps to replace the components in the baseline networks, and we found that the more functions it replaces, the higher performance gain it can achieve. Right. So I think that really shows that our design allows the network to adequately benefit from the pre-trained knowledge. The third part is we did lots of visualizations, such as the training curve, and then we also show the average language attention over all the instructions, and then we go detailed to show the layer-wise and step-wise attentions in transformers. So the attentions across the state representation, the language representations, and the visual representations to show that how this attention across these different modalities of inputs has been aggregated and evolves at different layers. And then finally, that helps to make a decision.
So do you have any unexpected or interesting finding?
I think I just briefly mentioned that when I talk about visualization. And yes, our visualization is very interesting, I think, very inspiring. So again, we can see how the attentions evolves at each transformer layer. Right? It sort of spread it out across all the tokens at the beginning, and then we can see clearly that the attention shifts to the most relevant part of the instruction and the visual features, and then it aggregates more and more to the most important tokens that helps to make a decision. So I highly recommend interested audience to look at our appendix for those visualizations.
Conclusion and future work section. How do you see the impact of the paper, and are there any interesting papers that followed it by you or other groups?
Yeah, I think the best thing is that we introduce this simple and effective idea that make the transformer to function as a recurrent network. And that really helps the model to make better use of the pre-trained knowledge. We actually gain huge performance comparing to previous model, which just used the pre-trained model for the input encoder, right? But here we use it as a navigator network, actually. And besides that, because the idea is simple and effective, so I think it can be applied to many other problems that require this sequential decision process. So yeah, I think it would be interesting to explore it to other tasks as well.
Can you give an example to such tasks?
For example, the most relevant one or the closest one, visual dialogue, which is human, and then the agent needs to discuss about an image. Right? So the human can ask questions or answer questions, and then this is a sequential decision process, and it's very important for the robot to know which question that has been discussed, like what information have been unknown in the past discussion, and how would that influence our new discussions. And then as for the question, are there any paper follow it? I think there's now only one citations on Google Scholar, which is a paper. It's like a survey paper that look into all the past state-of-the-art navigator for this vision language navigation task and compare them and to see where they perform well and why they fail. But I know there's the paper is getting lots of attention, I think, because many people from different groups around the world have been contacting me to ask for the paper, for the code, and it seems that they're quite interested in the method.
For the next PhD student reading your paper, what are the next obvious or things that you think are going to be impactful?
Yeah, so I think there's some quite interesting extension to this work. One is a better way to do pre-training, because now we just apply the network that is pre-trained on some general vision language knowledge and some very simple navigational oriented pre-training tasks. So I think there are much more better pre-training objectives designed out there that can be applied to pre-train this model and then get better improvement. So that's the first thing. And pre-training is, obviously very popular today in vision and language domain. So I think that is a good direction to go. Second thing is, it would be great if there's a way to improve the memory efficiency, because transformer is a very large model and consumes a huge amount of memory during training. So it would be great if there's any way that we can cut down this memory to make it much more efficient, and I think that would be very helpful, right? And especially if we extend this to the navigation problem, which requires much longer steps to complete, and this will be issue. The third part is, I think it's my favorite part, is the transformer is now being applied not just as a encoder to get better representation, but it's been applied to achieve many interesting purposes, such as creating a graph model, creating a topological map, and etc. And I think it would be very interesting if we can extend this recurrent BERT to achieve those interesting functions, and that would be great to just rather than just use a transformer to sort of brute force solving the task, we actually put more design, more reasoning into the model, and allow it to accomplish more interesting tasks.
So you said that you're doing all the experiments in simulation. So how fast is it? Is it something that can run in real time on an actual agent, or are we super far away from this being feasible?
Actually, it highly depends on the network. I haven't tested our network, but there are other researchers. They have deployed a network train in a simulator to a real robot in real world, and that works very well, I think. But their network model is smaller, so it can process with a much shorter time. But for a much more complicated network like ours, I think, I'm not sure. We have to experiment to find out.
So now to my favorite part of the podcast. What did reviewer 2 say? Can you share some insight or comment that a reviewer had that made your paper better?
Yeah, so about the comments, so most of the comment that we received are actually about justifying some design details, because I think it's quite a new design and it takes some time to fully understand it. And also about clarifying the experiments and visualizations. Honestly, I don't think there is any very tough questions in the reviews, but they did ask for additional ablation experiments, and we did those experiments and put them into the final version.
So what ablation did they ask for, and what was the what outcome did you see from that?
So the most important one, I think, or the one that interested most people, is that we have a sort of a trick to reduce the memory consumption during training, which is to only allow the model to do language self-attention at initialization rather than each step. And then we didn't do a very comprehensive ablation on that part, because there's a lot of things to try. For example, different batch size, larger batch size, but accumulate gradient, or multi-GPU training, so multi-processing, etc. So they asked for this, and we add those experiments in the final version. And I think that they're really good questions, which really help us to strengthen our arguments.
Thank you for listening. That's it for this episode of Talking Papers. Please subscribe to the podcast feed on your favorite podcast app. All links are available in this episode description and on the Talking Papers website. If you would like to be a guest on the podcast, sponsor it, or just share your thoughts with us, feel free to email talking.papers.podcast@gmail.com. Be sure to tune in every week for the latest episodes. And until then, let your papers do the talking.